In the last session on reasoning, reasoning 1, we talked about deductive reasoning, inductive reasoning, by which we mean reasoning from sample to population. To make things clear, because the word inductive is used in ambiguous ways in the literature. This is the way we are going to use it. Abductive reasoning. What that means is that in abductive reasoning there will be a theory, there will be a particular observation, let's call it a data point, and using this, oh, what? Just one self-elimination. That comes as a total shock to me. Because usually people complain that I'm a bit mouse. So something has happened.
But that's like Euclidean geometry.
And also please write little bigger.
Font size. It's not on the top.
I did. There is something that you have to do there. You want to call something? Because if I use the mic, there will be the same problem. Yeah. And not turned on. I mean, when I say mic, I mean the other mic. My name is Mohanan.
I'm not a loud mouth. I think you can carry on till it comes.
Yeah.
But clear.
No, it's not.
Okay, I guess just continue without. You did it for the recording?
Yeah.
No, you did it for the recording. Oh, there.
Now.
No.
No? Yeah, it's better. Huh?
Ah, okay. All right. Okay, so given this as your grounds, your conclusion will be an interpretation or explanation of the data point.
Font size.
Oh, okay, I'll try. So this is the nature of abductive reasoning. It gives you an explanation or interpretation of a data point, particular observation, on the basis of, you have to have a theory, and obviously the data point as well. The other reasoning that we didn't go through in detail is speculative deductive. And what speculative deductive reasoning does is to justify the theory itself. Here the theory is taken for granted. Here what you're justifying is the theory itself. That's the main difference. And other differences would follow from that. The grounds for this, the grounds for speculative deductive reasoning, let me write it there to make it as big as me. The grounds are a sample of data points, ultimate grounds, not the actual grounds here. A sample of data points, not one data point, and from that you come to observational generalizations using inductive reasoning. And use these observation generalizations to defend your theory. So what is defended is the theory on the basis of observation generalizations. If you don't have observation generalizations, you don't have a theory. How do you defend this? First you construct the theory. So the theory doesn't exist. Okay? You go from observations and generalizations to theory. How do you get there? You can say imagination, luck, intuition, speculation, anything. Sometimes you have a dream.
Can't one word would be hypothesis?
The word hypothesis used here. So I want to, hypothesis is right, but I don't want to use it. Also, sometimes people use the word hypothesis to refer to established hypotheses. They still use the word same thing. The only thing that you can say is conjecture. If you collect a set of conjectures, not proven yet, but you come up with the conjectures. That's a theory in science. Not just one conjecture, but a set of logically connected conjectures. That's what makes a theory. Okay, this is not proved yet. How do you prove it? You prove it by deducing the consequences. And that is deduction. If these conjectures are true, then certain results are true. These are the logical consequences. That's a deduction, which is why it is called speculative deduction, because it involves a combination of the two. This part is speculation, this part is deduction. It's not complete yet. What you have to do is to show that these logical consequences, which scientists call predictions, and what mathematicians call theorems, same thing. They match these observation generalizations. They agree. Now, if the two match, then you say the theory has successfully explained the generalizations. So, crucial to this is the idea of explanation in the way I have described it. Explanation is not making something simple and helping students to understand. Explanation means deducing the consequences and demonstrating that the consequences match what needs to be explained. You need to explain this. And this is how you explain it. By showing that the consequences of the theory, the predictions of the theory match. Match the observation generalizations. They're the same.
Yesterday's exercise was an exam of what we did in law of moments. Could we say that it was?
There was no theory. Law of movement is just this.
Just to make up the point, in a certain sense, from the observation generalization, you're building the theory.
Yeah.
And then from the theory, through the logical consequences, you're explaining the observations are true.
Yes.
Isn't it self-referential?
No, I'll show you why not. This is, in fact, this is the first question that people have. It looks cyclic.
Yes.
I'll show you why it is not cyclic. Okay. I have not yet argued. I have not shown you what the argument is. All that I said is, when scientists say a theory explains a set of observation generalizations, that's what you mean. Okay? So if the predictions of the theory are correct meaning they match the observation generalizations, then you say the theory explains the generalizations. But that doesn't necessarily mean we should accept the theory.
When we derive the relation between weight and length of the weight from the axis rotation, was it not a theory in just observation generalization?
It is just an observation generalization, not yet a theory. Because weight and length are simply two observable constructs, and you're simply stating a correlation between them. You're not explaining why that is so. I'll come to that in a moment. Okay? Yeah.
Is this the process we were following in the ethical inquiry?
Very similar process. Yes. Very similar, except what we have here are not data points. They are individual judgments, moral judgments, but the rest is the same.
The reasoning followed is on
Exactly.
these lines.
Yeah. Okay?
Having
Yeah.
said that, we didn't really get that far developing a theory of the initial.
No.
Go
But
down
this is the
that
beginning,
path,
yeah. This is just the third day. Yeah. Now, how do you now argue for a theory? I haven't said how that is done. I simply stated this is what scientists mean by explanation. The argument, speculative deductive argument, is also called explanation-based argument. And that argument goes like this. We have a set of observation generalizations. And these generalizations call for an explanation. You need an explanation. So you find an explanation that works correctly, and you look around, is there some other explanation? No. This is the only one, or this is the best explanation possible. Does the explanation have any problem? Does it make incorrect predictions? Is this a good explanation? You check very carefully and you say, yes, it's a good explanation. It does not make any incorrect predictions. And this is the best one. If it does not make incorrect predictions, and if this is the best one, then you accept that explanation. So in the absence of an alternative explanation, a better explanation, you accept the one that is given to you. But of course, when you come across a better one, you accept that. That's the argument. This is explanation-based argument. Okay, now I've stated this in a very abstract way. Let me give you an example of what this means. A simple example would be Einstein's explanation for this, okay? Yeah. Einstein's explanation for what has been called Brownian motion. And Brownian motion is like this. Someone called Brown, that's why it is called Brownian motion, observed that if you look at a droplet of water with a microscope, and you observe little particles, say for example dust particles or pollen particles, you find that these particles move around in random zigzag ways. So they kind of move, observe this, it moves there, and so on. That's very strange. Right? Unless the dust particle is alive, it shouldn't move. Given Newton's laws of motion, it should just, if it is moved, either it should be stationary, or it should just move in a straight line. Or if there is some other force, maybe, a circle, if there is going round and round something. So given Newton's laws of motion, this is strange behavior that calls for explanation. Well, one possibility is that, in fact, one thing that I tried with my students is that what you have here are demons, little demons. And of course they can move around, of course, but that doesn't make any sense for reasons that I will not go into right now. Einstein came up with the following explanation. That explanation consists of the statement that water is made up of water molecules. Notice that this argument was made at the beginning of 20th century when the notions like atoms and molecules were questioned. In fact, a famous person called Mach said atomic theory is nonsense, it is not scientific because you cannot observe atoms. And the person who was following the kinetic theory of heat, I think he committed suicide, right? Yeah. Because he was depressed. I mean, he knew it was a good theory, but this particular view of science held sway and wasn't accepted. So, assume that water is made up of molecules. This is one theoretical proposition which uses something that you cannot observe, namely molecules. Water is observable, but not the molecules. And I'm not going to write down all the details. The molecules have some freedom in liquid, molecules have the freedom to move around. So they keep juggling. Or moving. No, randomly moving molecules. Now, if the molecules are, if this is accepted, that the molecules, when they have energy, the molecules have some inherent energy, they keep moving. So here is one molecule, and that moves, and there is another molecule that is standing here. When they collide, this moves this way, and the other one moves the other way. And of course, here is another molecule, and the same thing happens. So they hit each other and move in different directions. That follows from the molecular theory of water and the energy. And of course, if you increase the energy by heating, the movement will increase. Now, what happens? These guys are visible dust particles, but these guys are not visible. So imagine this one goes this way, number 2, and somewhere here is the big one, the dust particle that you can observe. And it hits the dust particle moves that way, and the molecule moves this way. You observe the movement of the dust particle. Another molecule comes along and hits this, and the dust particle moves that way. And there are so many of them. So okay, imagine a huge basketball that is about 10 feet in diameter, which is being kicked around by little children. You cannot see the children, but you see the basketball, the big basketball, moving around, exactly like this. Okay, now, what was mysterious earlier, why is it that a non-living thing behaves like a living thing, like a butterfly or whatever, is now explained because of the action of the molecules. So, here is my explanation, right? The logic of explanation-based argument says there must be an explanation. And I'm saying I have an explanation. It makes the right predictions, and you have to accept my explanation unless you have a better explanation. And you don't. Okay, so you accept this. I'm not claiming this is the ultimate truth. It may turn out to be wrong, doesn't matter. For now, you have to accept it. That's the logic of scientific justification, essentially. Every theory is justified this way. This is the structure.
But this, again, when we say unless there is some other explanation, we are going to agree to
Absolutely.
this. So this somewhat resembles this abductive.
It resembles abduction, exactly. That part, unless there is a better explanation, or you can show that it makes an incorrect prediction, we must accept this. That part is exactly the same. What the two places where they're different is, yeah, in abduction, what you are explaining is one particular piece of data, one data point, and you already have a theory. So what that means is that unless you do this, you cannot have abduction.
Within the theoretical framework,
yes,
what is the best?
Yeah, and this statement that I just made, unless you have a theory, you cannot use an abductive argument, has huge consequences to academic research. Here is the consequence. Historical explanations, most of them are abductions. Unless you have a theory that justifies, or that is used as part of the grounds, the reasoning is invalid. So you have to ask, where is your theory? This is what Sripanna was doing in Sherlock Holmes. She was unearthing the counterparts of this. So pieces like X causes Y in general, and she used that to arrive at some conclusions. So quite often when we come up with historical arguments, we have some implicit theories, not clearly formulated, not justified theories, and we are using those theories to come up with historical inferences. But those implicit things will have to be made explicit and defended. It is not sufficient to make them explicit. In Sherlock Holmes, you are just making them explicit and then leaving it at that and say, we all agree this is true. But that is not sufficient in academic inquiry. We have to defend them.
So in the Holmes story, can we say that Holmes developed the theory using speculative deductive reasoning?
No, he appealed to common sense theories,
Which are existing.
which most of us kind of share without really thinking. These are unexamined theories. And Holmes was appealing to these unexamined theories, such as, for example, if you have a limp, then you exert greater pressure on the other foot. And we agree, yeah, this is true, we have seen it. This is a kind of common sense theories. But you haven't actually examined the theories in detail, critically evaluated them, looked at alternatives and so on. Those things are missing. So these are not academic theories, these are common sense theories.
In light of this, if I reflect back on the academic research, most of it is more of abductive reasoning, not really theory construction. Because
Now, when you say most of academic research, what you mean is some fields of academic research, not all fields.
yeah.
So, for example, the whole of mathematics uses just deductive reasoning; it doesn't use abduction or anything else. In theoretical physics, we use speculative deductive reasoning. But if you go outside of theoretical physics to other domains, in biology, for example, you don't find rigorous. To begin with, in biology, you don't have, examples of theory other than, for example, Darwin.
Yeah.
Or Mendel's theory. These are the only two theories that we know. But even those are not rigorously defended as they ought to be. And if you move from these two fields to other things, by and large theories are simply opinions
Rely on
and
physics and
speculations and so on, not rigorously defended. So take something like Freud's theory of psychoanalysis, which is not very different from mythology. And people take it seriously still.
Can you give an example which could bring the contrast between speculative, deductive and abductive?
Yes. So I wish I could have brought my favorite pendulum. I'll do that tomorrow. Why don't I do that? I'll demonstrate it tomorrow. Unless you see the actual explanation, it's not easy. I'll do that.
I'll remind you.
Yeah?
I'll remind
You
you.
okay? Thank you. That's what I was worried about. I say we'll do that tomorrow, and when I'm here, I may not have the pendulum. All right. So let me go through one more argument using speculative deductive reasoning to give a feel for what it is like. I gave an example yesterday, day before yesterday, using magnetism. And I think that is given in the document on reasoning that was distributed day before yesterday, whatever day. We briefly talked about heliocentric theory some time ago. And in the course of talking about that, we also talked about explanation for summer and winter within heliocentric theory. You can say it's a kind of sub-theory. Okay? Theories are quite often built up of smaller theories, and these smaller theories are made up of other theories. Or alternatively, you can say, when you have 2 or 3 theories, people kind of integrate them into one theory, larger theory, and then you integrate those into higher order theories and so on. So that's the sort of nature of theory construction. So you have a theory of optics, you have a theory of magnetism, then you have a theory of electricity. This is what you learn in school. Then you discover that these three theories come under a theory of electromagnetism. Maxwell was able to integrate what looked like apparently unrelated theories of optics, electricity and magnetism into a single theory. That was a success. And this happens quite often in theory construction. Individual theories are integrated into larger theories. One of the things that we have been trying to do is to construct a single theory of evolution, not only for biology, but also for culture and evolution in the physical systems. A transdisciplinary theory of evolution is this ambition, whatever, holy grail of integration, which drives theoreticians. You have the theory of electromagnetism, quantum mechanics on the one hand, and then you have theory of relativity. The holy grail in physical sciences is to combine the two into a single theory. People call it theory of everything and so on, but it's not a theory of everything, it's simply a theory that integrates these two into a single theory, and it is very difficult to do so because of contradictions between them. People haven't quite solved that problem. Okay, let me take something simple, the heliocentric theory. So let's begin with some observational generalizations, without which you cannot begin constructing a theory. So if you want to help students learn the art and craft of theory construction, that's where you begin. You don't begin with a theory, you begin with a set of observation generalizations that you want to explain. One observation generalization would be the daily cycle of light and dark. And by daily, I mean approximately 24 hours. So every child can see that it is light during certain period, and then it becomes dark, and then it becomes light again, and that time is approximately 24 hours. Okay. And you can also see that this correlates with the appearance of the sun. That is, when it is light, the sun is up in the sky, and the sun appears very close to the eastern horizon in the morning, and at noon the sun is up above our head, and in the evening the sun is close to the western horizon. Notice I'm carefully avoiding the formulation of the sun rises in the east. It means that the sun is moving. I'm simply saying the position of the sun, observed position of the sun, as we observe from the earth, from our point of view, is close to the eastern horizon, close to the western horizon, above our head. Observed position, in this case, I'm not implying a heliocentric theory or a geocentric theory. So this formulation will be acceptable to both Ptolemy and Copernicus. They would agree that this is true. When you have the debates between theories, when you have any debate, you have to identify the grounds that you agree on. So if Ptolemy and Copernicus are going to have a debate, they must have agreed upon grounds, and that's what I'm stating here. Okay, now, question, how will you explain it? Well, let's begin with Copernicus. Copernicus would say, what happens here is that the sun is stationary, doesn't really matter, but the earth, what does the earth do to explain this?
It moves.
West to east.
What kind of movement?
Rotation.
Rotation, not revolution. Okay? So the earth rotates, and then it appears to us as though the sun is moving. Right? So earth's rotation is the explanation. Alright, so here I have one observation generalization. I have given you an explanation, and then you can show how this one derives this result. I'm not going to go into the details. When we are doing this with children, I guess we have to use some electric light in an apple and see how it functions. You can use that kind of modeling. That is Copernicus' explanation. And if this is the only explanation available, we must buy this. Those are the rules of the game. This is the heliocentric theory. And Ptolemy is listening to Copernicus teaching in grade 6, grade 8, whatever. And he says, wait a minute, before you buy it, consider my theory. And my theory says the sun revolves around the earth. That will do equally well, right? So why should you buy Copernicus' theory? Unless you can show that the heliocentric theory works better, there is no argument here. There are two candidates and you cannot choose. This is the very first statement to make. And children have to go through the comparison before they make an intelligent decision. If you simply say the earth rotates and do not give any reasons for believing it, you are teaching science as dogma. As religion, there is no difference. It may be the case where believe this is true, that doesn't matter. What we believe to be true should not be taught as dogma. In scientific inquiry, you can do so in religion, not in science. So science, education, and religious instruction are not distinguished in our schools. Science education is done against the spirit of scientific inquiry. It causes the destruction of the spirit of scientific inquiry in our classrooms. The only way to get out of that problem is to provide justification for our conclusions and allow debate between competing theories. Okay, so that's one piece of, one observation generalization. There is another 24 hours cycle. Notice that we have been referring to these as periodic correlations. Not linear correlation, but periodic correlation repeatedly happening. If you draw a timeline, what you're going to get is a wave. The second one is the nightly cycle of the stars. So if you observe the stars at night, you find that the positions of stars keep moving. So for example, if you take a photograph, or if you're just looking, and one star is here, this is the northern hemisphere, let's say, and a little later you'll find the star is here, a little later the star is here, and so on. And you're going to find something of this kind. Each star will be moving in this. If you take a photograph exposure for a period of 4 or 5 hours, you're going to see these lines, and you can easily see them if you do a Google search. You'll see those lines, and you can do this. Children can do this if they have a camera that can be exposed to the sky, a clean sky at night. And then you find that there is a star that is not moving. I mean, moving not meaning moving with respect to us. That is called the pole star, or Polaris. Okay, question, why does it appear, why do the relative positions of stars keep shifting around the pole star? I've tried my best to avoid attributing movement to stars. I'm simply saying relative positions of stars.
They also.
That could be one explanation. Sorry? Yeah?
All of this was supposed to be done on another day in a 2-hour chunk. Today, before Madhav Singh, you're supposed to do probabilistic and feasible reasoning.
If there's no time for, so we can do that later in the afternoon. So continue with this, we'll...
I'm sorry. What I thought was people didn't quite understand speculative deductive reasoning.
That could complete it, that was coming late.
So what do I do?
Continue.
Huh?
There's no active reasoning. No, there's no reasoning. We can do it in the afternoon.
Do what in the...
We'll do diffeasible reasoning in the afternoon.
Diffeasible reasoning in the afternoon. Okay. So let me, I have a few more minutes. Let me give a brief flavor of the heliocentric theory. Yeah, I didn't look at the stuff that I had promised to do. Okay, so How do we explain this? I'm going to erase the observation generalization. So you ask Copernicus. Copernicus says very simple. The Earth rotates. So here is the Earth, and Earth rotates with an axis. Here is the pole star, and the Earth rotates. When it rotates, when you're looking at the sky, the stars around the pole star will appear to be moving. So if I'm doing this, and I'm not aware that I'm moving, so I'm standing, for example, on a rotating platform, and I'm not aware the platform is rotating, what I'm going to see is the lights above me, I will think the lights are rotating. And it is, the axis of rotation is passing through the pole star, so the pole star doesn't move, the other stars are moving. So it is the orange that is moving, not the sky. Ptolemy will say, but why do you need that? The stars are on a dome, stuck on a dome, and the dome is rotating, and that's why the axis of rotation of the dome is passing through the pole star and the Earth. Equally good. Okay? There is no reason to choose between the two. So, what does a teacher do? At this point, the teacher should say, there is no reason to make a choice between the two unless we have some other better, to show that the heliocentric theory works better. And there are many phenomena of this kind. We have to make a list of these observation generalizations and see what we can explain. And this is where the summer-winter comes in. I won't go into the details. You can give a good explanation for summer and winter by appealing to the rotation of the Earth, revolution of the Earth, and the tilt of the axis of the Earth with respect to the plane of revolution. You have to combine these three things. Crucial part here is the tilt of the Earth. I'm not going to, at this point, go into the details. When I bring this up in the classroom, students typically begin by saying summer and winter. There is the elliptical orbit of the sun, elliptical orbit of the Earth, and the sun is at the center here. And when it is far away, this is winter. When it is closer, this is summer. So it's a matter of theory of distance, and that can be easily taken care of by saying, if that is your theory, you will predict 2 summers and 2 winters. And students immediately see that and say, okay, let me modify my theory a little bit. Okay. The sun is not at the center. The sun is at one of the foci of the ellipse. If that's the case, then there will be summer here, but there will be winter here. That part is done. But if it is distance, notice that on top of a mountain is close to the sun, it should be very hot there, and at the valley it should be cold. That's not the case. I won't go into all kinds of details. This is something that has to be worked through very carefully. It's not simple. Then they appeal to various other things as well. I think we discussed this in the discussion forum. You can go back there and take a look. So I won't go into the details there. Crucial to the explanation in terms of the heliocentric theory is the idea that if you have a patch of light, and if the Earth's surface is perpendicular to it, or the patch of light is perpendicular, the area covered by the light is less than if this slanting. Here, the area covered is greater, so the energy is distributed over a greater area, and hence the heat is less. And Copernicus could make a case for his theory using summer and winter, especially when you have summer in one hemisphere corresponding to winter in the other hemisphere. That's a crucial piece of the argument. Let me just give one more crucial piece of evidence, and that is the Foucault's pendulum. And that is an experiment that was conducted. Astronomy is largely non-experimental. Okay, to say that experiment is necessary in science is ignoring astronomy completely. Physics is an experimental science because anything that physicists do, they conduct experiments. Biology has become, recently biology has become an experimental science. It wasn't the case earlier. But astronomy, right from its origins, has been non-experimental. Reason being, you cannot play around with planets and stars. You can only observe them from here, like an ornithologist observing birds from a distance. This experiment was done by scientist Foucault, not to be confused with the postmodernist Michael Foucault. What he did was he went to a cathedral with a very high ceiling, 60 meters or so, and hung a pendulum, heavy metal pendulum with a metal wire, and set it in motion. The reason why he did it was he wanted the pendulum's motion to be unaffected by the Earth's rotation if the Earth rotates. So if you have a pendulum on Earth right now, when the Earth moves, the pendulum will move with it. So he wanted to liberate the pendulum from that. That's why he took such trouble. And he set it in motion. So imagine the pendulum moves from there to there, several meters. You can see this pendulum, a version of this in Ayuga here, but they have to do some extra stuff like some pulses, continuous pulses, because the pendulum is not that big. So the pendulum will keep moving. And when they observed the pendulum, they discovered that the plane of movement kept shifting. So it started this way, and then it moved this way, and moved this way. And then it kept rotating and came back to the original, the plane of the pendulum movement came back to the original position in 24 hours. Why should it do that? That's something puzzling. Right? What is the force that shifts? Well, there is no force, according to Foucault. You don't need a force. What happens is, the pendulum doesn't change. It is us that is rotating. So what we observe as the pendulum changing its plane of oscillation is simply the Earth rotating. So we have an explanation. Under the assumption that the Earth rotates, there is an explanation. But had Ptolemy been present during this experiment, it would have been very difficult for him. In fact, I can't think of any explanation that Ptolemy could have given for this fact. So Ptolemy would have had to accept, yes, you have an explanation, a good explanation. I don't have any explanation, therefore I have to buy your theory. Okay. This is the crux of argumentation for theory in science. Right. That's speculative deductive reasoning. If you're doing this, there are a few things that I have skipped, namely the things like the retrograde motion of planets. That doesn't mean the planets are moving in this retrograde fashion. What it means is that from observers on the point of view of the observers on the Earth, if you keep observing the positions of planets, so let's say these are planets, these are stars, and stars' relative positions do not change, even though all the stars appear to move in a 24-hour cycle. If this is a planet, the position of the planet keeps shifting with respect to the stars. So you find this planet here, a few days later you find the planet here, a few days later planet there, and so on. So this is the kind of movement that you observe, movement with respect to the stars, or rather relative shift in observed positions, to be very precise. Then you find that at some point it does this. It seems to shift in the other direction. So this is the retrograde motion, backward motion, and then the planet goes back to the original movement again. So why should planets do that? Was the question. And Ptolemy noticed this, and in fact, this was known even during great times. And the word planet means wanderer. Planets kind of wander. The positions are not kept fixed. Stars, on the other hand, have very fixed positions relative to each other. The sun is a wanderer, unlike stars. Therefore, for Ptolemy, the sun was a planet. So meaning of the word planet, notice, has shifted from the Ptolemaic time to our time. They don't mean the same thing. What is the explanation for that? Okay. Students find it somewhat difficult to explain, understand and explain retrograde motion. Every time I have taught heliocentric theory, I've had extreme difficulty in communicating the explanation to students. So we need to find, I think I have come up with some idea now, but I still find it somewhat difficult. Not easy. Okay, this is the good time to stop. Notice that the entire thing was an exposition, right? I wasn't doing inquiry-based learning pedagogy.